At first glance, wind turbines seem like an obvious engineering problem. If blades capture wind, then more blades should capture more energy. So why do almost all modern wind turbines have exactly 3 blades? Why not 2 for simplicity or 4 for extra power? The answer is not aesthetic. It is the result of physics, efficiency, stability, and decades of testing that narrowed the design down to one surprisingly balanced solution. Wind turbines work by converting the kinetic energy of moving air into rotational motion. The blades act like airplane wings, generating lift as wind passes over them. That lift turns the rotor, which drives a generator. The key detail is that turbines do not extract energy from the wind evenly. Each blade disrupts the airflow behind it, creating turbulence called wake. Too many blades increase interference. Too few create instability. Two-bladed turbines were tested extensively, especially in the early days of wind energy. They have one major advantage: they are cheaper. Fewer blades mean less material, less weight, and lower manufacturing cost. They also spin faster, which can seem efficient. But speed creates problems. Two-bladed turbines experience a phenomenon called gyroscopic instability. As the turbine rotates and changes direction with wind shifts, uneven forces act on the blades. This causes vibration, stress on the tower, and fatigue in the structure. Over time, this reduces lifespan and increases maintenance. Two-bladed turbines are also noisier. Faster rotation creates more aerodynamic noise, which becomes a serious issue near populated areas. Visually, they flicker more aggressively, which affects acceptance and zoning. Engineers found that the savings in materials were often lost in structural reinforcement, noise mitigation, and shortened service life. 4-bladed turbines were also explored. Adding a blade increases solidity, meaning more surface area interacts with the wind. At low wind speeds, this can increase starting torque. But once the turbine is running, extra blades become a disadvantage. They increase drag. Drag does not help generate power efficiently. It slows rotation and reduces the optimal tip-speed ratio, which is the speed at which blade tips move relative to wind. Wind turbines are most efficient when blade tips move several times faster than the wind itself. Too many blades lower that ratio and reduce overall energy capture. 4 blades also mean more material, more weight, and higher cost, with little to no gain in energy production. So engineers were left with a trade-off. 2 blades were cheaper but unstable. 4 blades were stable but inefficient. 3 blades landed in the middle. 3-bladed turbines rotate smoothly, distributing forces evenly around the hub. This symmetry reduces vibration and mechanical stress. The rotor remains balanced as it turns, which improves durability and lowers maintenance. 3 blades also achieve an optimal balance between lift and drag. They capture a high percentage of available wind energy without excessive turbulence or interference. The tip speed stays within an efficient range, producing strong power output without excessive noise. Another factor is control. Modern turbines adjust blade pitch to regulate speed and protect the system during high winds. 3 blades allow for precise control and braking without sudden imbalances. In extreme conditions, the turbine can feather the blades safely, reducing load on the tower. With fewer blades, control becomes harder. With more blades, response becomes sluggish. There is also a human factor. 3-bladed turbines appear visually smoother and more stable. Studies showed that people perceive 3-bladed turbines as less chaotic than 2-bladed ones. This mattered when wind farms began expanding near communities. Public acceptance influenced design choices just as much as engineering constraints. Importantly, 3 blades do not extract all the wind's energy. No turbine can. Extracting too much would stop airflow entirely, which would halt rotation. Wind turbines are designed to let air pass through while slowing it just enough to transfer energy efficiently. 3 blades achieved this balance consistently across a wide range of wind speeds. That is why the design converged. Not because engineers liked the number 3, but because physics narrowed the options. When cost, efficiency, stability, noise, control, and lifespan were all considered together, 3 blades consistently performed best. Other designs still exist for niche applications, but for large-scale electricity generation, 3 blades became the standard because they solved the most problems at once. Once you understand that, wind turbines stop looking arbitrary. They look optimized. The number of blades is not a tradition. It is the result of eliminating every alternative that worked less well. If you enjoyed this explanation, the next story explores another everyday design choice that looks simple but is actually the end result of decades of quiet engineering decisions. Click on the channel to discover more untold stories behind simple things.